Please join me in welcoming our next speaker, Kamil Witecki. Kamil, the positive fog. Okay, so something about Kamil now. Kamil, the positive fog, you can tell he got his mind upside down, and instead of digging deeper into why the problems, he focuses on the solution and how to address the situation in the future. He focuses on the how to address the situation in future, but in his spare time bakes and watches B-class movies as a niche fan. He considers himself an average folk that anyone can approach. Proud of not developing any single programming language and helping to kill few, as he considers it not worth the effort to replace a perfectly good hammer with a fancy RGB hammer that costs a lot and provides the same functionality. If you do it for fun after hours, do it though. Hobbies can make no sense, says a guy who enjoys replacing timing belt in a 20 years old car. Worked for Nokia for over a decade and lately decided to help Snowflake look after your data and analytics. If you look closely, the largest common denominator between the two jobs is probably snow. So now, let's welcome to the stage Kamil Witecki.
Thank you very much. I'm very happy that you joined the room and you want to hear something that I want to say. Yes, I'm Kamil Witecki. Currently, I work for Snowflake as a release engineer. And I would like to say a few words about design by contract. And I wonder why you would like to hear something about design by contract. So I would like to ask you a few questions, and it will help me figure out what to put emphasis on. So would you like to write better, more reliable software? If so, raise your hand, please. Right, more than half of the room would like to create more reliable software. That's good. Would you like to run your unit tests, not only in your testing environment, but also on customer premises and whenever customer runs their workloads? If so, raise your hand, please. Okay, not so many people, only a few, like 1/4, 1/5 of the room. That's less than I expected, but maybe I will be able to convince you why is it worth to change your mind. Hello, everyone who joins, be welcome. And before we will start, I would like to highlight that everything that I will say is my view and it's for education purposes only. These opinions are not in any way associated or affiliated and endorsed by Snowflake or Nokia, who is organizer of this conference. And the message I want to send you, it will take around 30 minutes for the presentation, and then we'll have time for questions and answers. If you have any questions, we'll have dedicated time for that. There is no need to raise your hand during the presentation unless I ask you for that. And there is no need to shout. We'll have quality time to do that. By doing so, you are helping me to keep my flow and stay focused. And you are also helping others who might have their questions, and if we would be asking them one over another, it might not work very well. So, as I said, we are here because we want to create better, more reliable software in the end. And if we do not follow some rules, we'll end up with something that looks more or less like this house on the screen. Something that is falling apart, something that wherever you touch it, you have no idea where something will fail. And as with any construction, there are people involved in that, and there are people who will be maintaining it, and there are people with whom you will cooperate. So making this contracts or building the house or software is not only about software engineering. Engineering is also about human-to-human interaction, and by that you can address if you will be creating something like that or something that thrives and survives the test of time. And contracts are about three things. So in any contract, in any process, we have input, we have something that processes that input, and we have output. And we'll be making contracts about all these three things. So we will be checking our input if it meets our quality, and we will be checking our output if we are delivering what we are promising, and also invariants of that process if we are actually doing what we think we're doing. And last but not least, remember that this is just one tool. Do not try to overuse it. It's very good, and you will find many uses of contracts, but in the end, it's only about that. And don't try to force it. It's not about validating data that comes from users, for example, or from UI. Be sure to select a tool that matches what it is designed for in the end. So look for the tools that you have. In the previous speech in this room, you could have heard about Solid, and I will be making references to Solid so that you can see how this plays together nicely. Who knows something about Solid rules? Raise your hand if you do. Awesome. More than half a room already knows something about Solid. That makes me feel that we can continue with this one and that references will really hit good ground. So thank you very much for being interested in the topic and being interested in making reliable software. There we go. We'll start with something called cargo calls. Anybody familiar with the term? Less than half a room, maybe 1/4. Long story short, there were indigenous people living on islands, and this story dates back to 19th century. At the most prominent example of cargo cultism is from Second World War. So we are in the Pacific Ocean. There is an isle. So far, it was isolated from any civilization. And one day, there is a plane going over that isle and dropping something. And the tribe that lives on that island approaches that and sees some crate. And there is a writing cargo on it. And they look inside the crate and they cannot believe. They are so lucky they found food, they found blankets, they found such a treasure. And they started believing at some point that this treasure comes from gods. So they started praying, they started building fake landing strips, fake docks, so that more cargo comes. And guess what? Cargo was coming. So there was more cargo, so they started doing that more and more and more and more, and cargo kept coming. They were given food from the sky. How lucky they are. The gods are on their side. But one day, there was no cargo. What happened? They believed that they made a mistake, that the gods are somehow offended. What now? They started praying more because they need to somehow make it up to God, so they get that cargo. The problem was, Second World War was over, and nobody was serving cargo anymore because cargo was for troops. Do you see where the mistake is? They didn't understand where the cargo is coming, and they made some assumptions about it, and in the end, it turned out that their assumptions were wrong. There were no gods, and nobody was really offended. Cargo stopped coming because the circumstances changed. And we do the same about software. Anytime you look at software and see, okay, that function returns false if I do this parameter, so it will always return false, you are doing cargo cult. And I am guilty of that as well. I did that many times, so no blame on you. I'm doing the same. But in general, we should read documentation and we should make some kind of contracts. The issue of these people was that they never asked where that is coming from. They made an assumption it's coming from some kind of a deity, and they didn't have a contract that they will be praying and they will be receiving. And when I am asking if I do this, I send this parameter and I receive something back without checking if that really is what is intended, I might one day discover that things change. For example, I might not know that there was some buffer. And one day, instead of receiving a result, I might receive an error. Queue full, try again later. This is why we shouldn't test and then repeat what we did, but we should make contract. We should figure out how the thing works, or ask the other person, hey, how it works. Can I count on you? we need to stop cargo calls. And when it comes to stopping cargo calls and making some kind of contracts, there are three types of contracts. It's preconditions. Preconditions is me telling you what I expect from you. So I am expecting from you, bring me cargo, bring me food, bring me something. Bring me proper pointers, bring me proper objects, bring me values in that range. That will be preconditions, and I will be validating it. So if you send something wrong, sorry, I will not handle your request. Then we'll have post conditions. If I have expectations from you, well, you will have expectations towards me, of course. And I promise to deliver back. If we are doing contracts, you are keeping your word, I should be keeping mine. And last but not least, invariants. All that can work only if I am sane. So when it comes to people, my contract with you is that I expect you, for example, not to ask questions during the presentation. I expected you to come to this room, for what I am grateful, and you are expecting from me that I will deliver the speech. That's all is under the precondition or invariant that my internal state is sane. So if I would have a heart attack, I wouldn't be able to deliver no matter what you do. And no matter how much I want to keep my promise. So if my internal state is broken, we cannot do that. And that's why we need to check internals of the implementation if we really are still sane. And there can be cases when input is good, but we cannot produce good output because our internal assumptions got broken. And when it comes to contracts, I mentioned that this is about people. So we will be checking it internally in software. It will be embedded there. It is important that we understand what kind of communication style that is. Have you ever been to this kind of training, like soft skills training, that is about communication with other people? If you did, raise your hand. I have been to plenty, really. All right, less than half a room. I thought there will be more people. So in this kind of training, they would teach you that there are 4 basic communication styles. Aggressive, obviously, I tell you what to do and you better do it. Passive-aggressive, when I kinda puff about it. So you don't do the way I expected you to do, okay, and you expect me. And then there will be totally passive, like, you do nothing, you really don't communicate with people. And there will be assertive style. In assertive style, you set your boundaries, you tell people, hey, don't do that, or hey, I would like you to do that. And you also keep yourself accountable. When you say something that you will do it, you do it. You keep up to your promises. This is exactly the same thing about communication between software pieces, but also software teams. And when it comes to talking to other people, well, soft skills training is something to attend. And this is assertive communication for software and programmers. I will be using some framework here. And I mentioned different tools, and this is one tool. Non-virtual public interface. There was a proposal for C++ to introduce contracts in the language. It didn't pass, so it was not introduced. And I decided not to show it for another reason. If you follow this kind of an example of framework, you can then translate it to different languages. And in this case, we have very simple class that has one function that does something. And you will notice that the interface is not public. Sorry, of course, it's not virtual, it's public, but it's not virtual. And what is virtual is private. And by this, we can use that non-virtual final thing as kind of a template. And it will impose some limitations on each and every class that substitutes it. So this is first tool in our toolbox that we will be using. And I want to use it because then if you use Java or you use, I don't know, Python, you can still follow the same principle. So first, preconditions. I expect from you. And what kind of preconditions we can have, and what will happen if we don't really play assertive game here. So very simple case. You have a function, and it should operate on a well-defined object. An object that was already constructed, that wasn't destructed. You take a pointer to it, and guess what? Somebody passes you a null. What to do about a null? Of course, it's simple. I check my input, okay, it's a null, so I will return 0 for a null, let it be, because I didn't think about it, but I need to do something about it, so let it be 0. Or maybe I will return optional, and when I return optional and it's empty, then it means that parameter was wrong, but if I return some value, it's good. We start getting defensive. Like somebody throws something at us, we didn't have idea, but we try to do something about it. Like something that not really well thought things, just playing it by ear. So next time somebody sends you a pointer that points to the code section and not to the data section of memory. So what do? You can revert to API of OS, check that thing, figure out it's a code, and again use that optional. You see, we're entering some kind of paranoid area. So next time somebody sends you a pointer to a class that was to an object that was already destructed, what do you do about this one? You frankly cannot do much about this. So this would be defensive style of programming or passive style of programming. Somebody throws something at you and you just try to cope with it. But really you don't have good way of coping with it if you are trying to address each and every scenario in some sane way. Some situations are just insane, like an already deleted object. You cannot do anything valuable with that. Returning optional might not even be the case. What you want to do about it is express your expectation. Hey, I will work, and these are my conditions. You give me a pointer to a well-defined object well in its lifetime. It cannot be under construction, it cannot be under destruction, it must be well in its lifetime, and that's it. This is your precondition. All that we're saying about, like null pointer, pointer to a deleted object, whatever, becomes something that you just verify. And if it fails, you need to do something about it. The problem is what to do about it, and we'll get to that. What is important that you do it as soon as possible. So you want to verify it right before calling the actual implementation. And this non-virtual public interface idiom gives us a very good tool for that, because we have it and we can insert it in the right place. You will notice that I made that assert preconditions virtual. And this is because of Barbara-Liskov substitution principle. If you are familiar with Solid, you know already that Barbara-Liskov substitution principle tells us that if you have any object and you want to replace it, substitute it with something else, that thing must be indistinguishable from the original one. So for example, if I have a, I don't know, object that takes some parameters, the descendant one must take exactly same ones. It might extend that range, but it cannot move it or it cannot shrink it. If the range accepted is from 0 to 255, it can extend it to unsigned integer or signed integer, because all these values will be inside of that range. But if you try to move it, like I will not accept value 1, then you wouldn't really follow the rule. The problem here is that if we create a descendant class that extends that range, it must be virtual, because we want to extend it also in the assertion. And you might be wondering what to do when we discover that something fails. So what do I do now if somebody sends me a null? C and C++ has a macro called assert. I don't like to use it for different reasons. First of all, it's an atomic option. It kills the application, aborts it, and that might not be what you intend. You might have something that better. You might somehow cope with that situation. And other thing that standard assert does, it gets removed in the release compilations. And I like my tests to be run in each and every scenario. I wouldn't disable it for customer. If my software fails at customer's premises and somebody passes a null pointer that I am not ready for, I would rather have my assert fail and tell me, hey, this failed here, I expected something, it wasn't delivered. I get a lot of context. And if it's disabled, it will give me a cryptid crash somewhere in that executor even further. So for these two reasons, I like to replace original CAssert with something else. First of all, I would be throwing an exception. And I will be catching way more context. So one thing is catch your closest context, where we are, what file, what line, what we were checking, but also what is up in the stack, who called me, because it's frankly on the caller side, what we are checking here. It's not that function. It doesn't do anything about these parameters. It just verifies it. So we need to go up in the stack. We need to check who called it, where that call is from, and look for error there. So for these two reasons, I would replace standard asserts with exceptions. And we'll later see, I will give you some examples, where these exceptions can be useful and how we can deal with it. So this is about preconditions. Then we have postconditions. I expected something from you. Now you want me to deliver. So it's my time to give you what you asked for. Of course, if you will be asking me to lower my expectations, I will be telling you, hey, I will not give you much. So postconditions hold only if you kept your promises. If you lived up to preconditions, I will live to whatever you expect from me now. And again, in the same framework, we will be checking that internal implementation later on at the end of this function. So this will be last thing we will be checking. I did calculation, I verify if I am following my own contract. I am verifying if what I am offering you back is really what I promised. Because if not, then I am sure that there is some error in my implementation. And as soon as I discover it and I fail, I get the most context. I get whole information where that failed. I am as close as possible to the possible issue. So I know that preconditions were met, postconditions do not hold, the error might be somewhere in that one line. It might call a lot of different functions, but I get as narrow view as possible to figure out that error. And last but not least, invariants. And invariants are about our internal state. So as I mentioned earlier, if I will get heart attack, I will have hard time to deliver that no matter how much I try. And it's the same about software. If somebody overwrites me memory, if somebody in language like Python, where you might not really force private parts, somebody might just change something that you didn't expect to be changed. It was supposed to be private, somebody disrespected it, and it will not work. And invariants will follow the same thing. We'll be checking invariants, and we'll be checking them at the beginning and at the end. Why in that order? First of all, we want to be sure that we are sane when we start doing something. In general, preconditions might rely on the state. So sometimes you might expect your caller to do something before, like initialize me before you give me this kind of parameter. Or use a token that I have issued, so you will have some references of the tokens. And you need to check invariants prior, because if you will discover that your memory was overwritten, somebody messed up your internal state, then you want to be sure about it as soon as possible, because otherwise you would tell that the error was in the caller side, while in fact it was your invariant that got broken. And then you want to assert your invariants before you check postcondition. Because if you destroyed your own invariant in the middle of processing, don't blame the result. There is some error in the code that broken your own expectation towards your own code. So it's better to figure out first what went wrong that I destroyed my own invariants, because if you are not sane, if the class object is not sane, it cannot deliver proper value back. Now, what kind of invariants we might have, what kind of preconditions we might have, what kind of postconditions we might have. I have mentioned that I would like them to be run in customer premises as well. So one thing is what I mentioned before about these pointers that are given and so on. Some of them might be very hard to compute, very intensive in terms of CPU time, in terms of memory use. For example, let's imagine that this function, in fact, is doing some kind of statistical, I don't know, analysis, or it's returning some value that is random. And in the end, you want to verify that it returns a value that is somewhere in a range, and consequently values are uniformly distributed in that range. To verify that, you cannot really do that in one call. You need to have some kind of history, and you need to accumulate values returned over time and verify them. That might require you to collect many samples, that might require you to calculate a lot of things, and depending on what kind of application you work on, that might be okay, you might keep it in customer code, or it might turn out that it is too heavy. Like you are writing software for embedded device with a little RAM, slow CPU, and then it might not be something you can really afford. By the way, how many of you are dealing with such small devices that have very little RAM, very little CPU? I know Maciej. Who else? All right, there are few of you. So this is especially for you. You might consider some assertions heavy. And in that case, I like to introduce two different macros or two different functions. One is heavy, assert, and one is assert. And in your compilation, you are taking a trade-off. The heavy ones, you will be removing from the customer code because you cannot afford to do it there. But the lightweight ones, you will keep there. So in any time something fails, you will learn about it as soon as possible and with as much context as possible. And I have also mentioned that I like to throw an exception instead of aborting. If you imagine an application like Node.js or any other one that has an event queue and processes them one by one, and now something fails. Like there is a class that has broken invariant. It might happen. That object is broken. If it aborts the application, it aborts the application. You do nothing about it. You need to restart the whole server, whatever that is. And if you can catch it on the level of your event queue processor, then you might just look at that, okay, that object is broken, recreate that object, but continue with other events that you still have on queue. So you do not need to restart the application immediately. You can do something about broken invariant. And, well, I propose to use the tools that we have and not go straight to killing the application because one thing failed. We might be dealing with something that we can recover from. Of course, if your application is take an input, throw an output, finish, like implementation of grep or another tool like that, then original assert is good enough. If you are doing an application that is supposed to work for days, months, years, maybe it's too atomic option. And in that case, throwing an exception, catching it, analyzing where it came from, what class, what object was problematic, what was broken, might save you some time and might keep it up for longer. And when it comes to invariants in particular, there can be different ones. As I said, this is about internals of the class. It's not about who calls, it's not about return value, it's about state. It's about if I am sane enough. And they will be totally different. Even the same interface implemented by different classes might have totally different invariants. For example, with that event queue, in one case, it might be an embedded software version that is having some kind of a socket accepting connections, some kind of a small buffer that is keeping events in that buffer for processing, and the invariant might be the socket is open only when my buffer is not full. And that will be my invariant. I want to close that socket as soon as possible because, well, in that case, TCP/IP stack takes care about me and will tell that, hey, that wasn't delivered to the operator. And then when you see that the buffer is not full again, you have some room, you open the socket again. And that's the invariant of that class. You want it to close the socket if it's full, open the socket if it's not. But you might have totally different implementation that you will be using in different application, but using the same interface, accepting some kind of input, and you will have indefinite socket. Or you might store them in database, whatever, and that invariant will not hold. So invariants are specific to given implementation. And preconditions and postconditions, they have to deal with Barbara's list of substitution principle. So we cannot narrow down what we accept. We need to accept exactly what the original class did, or more, but not less. We cannot shift it, we cannot narrow it down, we can extend. And with the return values, it's opposite. Because if original class was returning only values from 0 to 100, and somebody gives me 101, what do I do about it? I have no idea what this is. We need to take into account different aspects of what we are doing and different use cases. We need to follow different tools. And in that case, how the class is used can be verified by preconditions and postconditions. And our postcondition expressed in the original class will hold for each and every implementation. And we can enforce it already at the very bottom and figure out that our descendant implementation is not following the contract. So it will be not up to somebody who implements later on the next processing stage to figure out, hey, I don't know what to do about it, but the contract will fail itself. And we will figure it out on our end, and we will keep ourselves up to our promises. So to wrap things up, we want to have software that is reliable. And by doing contracts, we are ensuring that different pieces of software play together well. So this is a piece that delivers something and expects something back, and I am the piece of software that is following that contract. And thanks to that, we can be sure that it will not be crumbling. And when we are changing software, it will keep us honest. So I might be changing that implementation of event queue, and by mistake, forget to close the socket that I mentioned. Checking invariant in each and every call will save me from figuring that out in production. It will figure that out as soon as I run software. No matter it's test cases, no matter it's in customer premises, no matter where it is, it will give me a signal and it will tell me this precondition got broken or this invariant got broken. Then contract is about three things. Two of them have impact on external world. Preconditions, checking what I receive. Postconditions, checking if what I give back is what I promised, but also invariants, the internal state, the sanity of the object itself, the sanity of the process itself, and it's as important as the input and output. And last but not least, please remember it's just one tool out of many. Use them together, like with Solid, like with different idioms, because they play well. And if you go around and pretend you have a hammer and everything is a nail, you might be tempted to try using assertions to test values received from UI. That might not be the best strategy for your customers in the end. That's all I wanted to share with you. And if you have any questions, I'm open, and we have time for that now. And if you figure out that you want to ask something later on, you can contact me by the email visible on the screen right now.
So, any questions on the whole?
Raz. Kamil, thank you for your presentation. It was quite refreshing, because for the whole day we had endless embedded space, very restrained systems that can do much, they have LLM and stuff, and here you come with virtual functions, exceptions, and all the other high-level features. I have a question about the, honestly, it's kind of inspired by my current position. We work on hard real-time systems, and our current approach is that we don't really have time to do all these asserts in real time. So if function or class gets garbage in, it should print garbage out. There's no time to honestly check anything, or in most cases, we definitely were not allowed to crash the application with the assert, and probably not even print error message. So it's quite restrictive. Do you see some way to, some compromise between these approaches?
It sounds like in your case, and let me repeat if I got it right. So you are working with a hard real-time system, and you are so concerned about CPU time that you cannot really pay any attention to input. If you receive garbage, you will return garbage, but it's by design like it should work to save resources.
Yes.
Okay.
Exactly.
That sounds, I mentioned that I like to have two different types of asserts. Heavy asserts removed from production code, and lightweight asserts that stay in production code. In your case, every assert is a heavy assert. So you keep them in testing environments, validating these preconditions, and later on you remove them. That's this kind of project where you really need to go very far with taking trade-offs. But having this run in a testing environment, well, it gives you test cases that are embedded in your code. Somebody tests a function that you didn't even think about it, that assert might catch it.
Okay, thank you.
Hi. So my question is, I'm here. Are there any other ideas how to implement this kind of contract in C++, like, I don't know, using templates or like error codes? Because you mentioned exceptions and asserts, which they have disadvantages. I was just thinking if there are any other options.
There can obviously be different options, and you might use something like return value being any or variant and returning error codes. That's a viable option. It will depend from project to project. In general purpose projects that do not have heavy constraints, I would just use exceptions. If we can use exceptions, this is a tool to do that. This is an exceptional situation. If we are going to a territory of hard real-time software like before, we might do nothing about it and we will be just removing them. And in test cases, we can as well use C assert and crash and have the debugger attached in that very place. In your case, I understood you're somewhere in the middle of this world. Like you have a software that is constrained, so you cannot probably afford exceptions. But on the other hand, you can keep the checks in the code. Did I get it right?
Yeah.
All right, so in that case, returning some kind of error code variants, that might be an option. The problem is bubbling that up. If you have very long stack, you will somehow need to reach a place where that can be handled. And the problem with that approach is that on each and every stage, you need to remember about it. Maybe that's an option, maybe not. Hard for me to tell. I wasn't in that situation.
Thank you.
Any other questions?
Thank you, Kamil, for your talk. My question is because sometimes I think that we can also make contracts using proper APIs. For example, on your example, when we don't want to handle the null objects or null pointers, it's sometimes much easier to actually pass parameters by references and actually don't care about if the user will call it wrong way. It's not my business. And my question is, do you know many other hints to creating a proper API when we don't have, as in these examples, when we don't have enough CPU or memory to actually create many contracts like in your presentation? Thank you.
That's a very good point, and I would consider it very similar tool. When you are writing in a software that is statically typed and can verify already on a compilation level, then do it. For example, if you accept values only from 0 to 100, don't use integer, use byte. In case you don't want null pointers, yes, use references. When it comes to hints, I would have to think about it. I don't have ready-made list. So when I'm programming something, it comes naturally. Like I am looking through boost and okay, this is something that I would use in that case. Not to mix up different physical values, physical units, I would use proper library. Very good point. I didn't think to include it in that presentation, and thanks to your question, we had it.
Any additional questions? Okay, so I think we can thanks to the Kamil for the lecture.
Thank you for coming.